Hey guys, here's another video on using SOHCAHTOA inside of right angle triangles. So hopefully you've checked out the SOHCAHTOA introduction and maybe the video on finding angles as well. If not, maybe a good idea to check those out. In this, we're going to be looking at how to find side lengths, again using SOHCAHTOA. So first of all, there's a different way that we can display SOHCAHTOA. We can put each of the lots of three letters inside these formula triangles. Now you might have seen triangles like this before. For example, if you're doing speed, distance and time, or density, mass and volume. There's quite a few other places where this sort of triangle helps us out. So if each of the lots of three letters is put in its own separate triangle. So if we look at the SO triangle, we've got SOHCAH and TOA. Now how these help us is if we cover up the chap that we're looking for, we're left with the formula. So in this top left triangle, if we cover up the S, that tells us that sine theta is equal to the opposite over the hypotenuse. If we were looking for the opposite, then we would cover over the O, and that would tell us that O is equal to sine theta times H. Although I much prefer to use it and would recommend using it as H sine theta. Exactly the same thing though. Just very important to realise that the H can't multiply the theta, the angle. Sine theta is completely separate to H. So to avoid that confusion, I would definitely recommend writing it as H sine theta. And then finally, if we were to be looking for the hypotenuse, we cover over the H, and that would leave us with the hypotenuse is equal to opposite divided by sine of theta. Okay, so that works exactly the same for the other three triangles as well. So let's have a look at how to use them. So, first step, as with finding angles, label the sides of the triangle that we're dealing with. So over here, the x is going to be the opposite, and we know the hypotenuse. Now again, I would recommend not labeling anything more than what we need to use. So we could label the bottom side as the adjacent, but we don't know anything about it and we're not looking for it, so we don't really care. So that would tell us then that we're dealing with SO. So the triangle would be this guy, and we are looking for the opposite. So if we were to cover over the opposite, we would be left with sine theta times H. So this tells us then that O is equal to 9 lots of sine 30. And then we just whack that in our calculator as is written down here in the bottom right. 9 sine 30, and that would give us 4.5. So we can do it without the triangles as well. So let me just demonstrate that. Obviously you don't have to use them, but whilst you're still learning trig, they probably are quite helpful. So let's just have a look at how we would do it without the triangle there. So we could start off by writing straight away sine 30 equals x over 9, and then to get the x on its own we would multiply by the 9. So we'd get 9 sine 30 again is equal to x. The triangles just help us to cut out algebra. Doesn't matter which way around you do it. So dealer's choice, up to you. So let's have a look at another one. Okay, so first up again, let's label the sides. So the side x that we're looking for is going to be the hypotenuse, and this bottom guy is going to be the adjacent. So our triangle would be CAH, and we're looking for H. So if we cover up the H, that would tell us that is equal to the adjacent divided by cos of theta. So we would get 10 divided by cos of 50. And then again, if we work that in our calculator, that will give us our answer. Again, with trigonometry, be very careful about what degree of accuracy the question is asking for in your answer in terms of decimal places and significant figures. Trigonometry is a very common area to be tested on those two things. Again, let's have a look at doing it without the triangles. Now this is really the sort of question where the algebra is messiest without the triangles, because the chap that we want is on the bottom of a fraction, but we can still do it. So if we used our cos identity, we would know then that cos of 50 is equal to the adjacent divided by the hypotenuse. Now the troubling thing here is that what we're after is on the bottom of a fraction, so we would first of all multiply by x, so we'd get x cos 50 is equal to 10, and then I'm going to overlap the picture a little bit, sorry. So then to get x on its own, we would divide by cos of 50, and again get x equals 10 divided by cos 50. So that's really when the triangles help us out, if the thing that we're after is on the bottom of a fraction. However, there is a cheeky approach to it as well. You may well notice that from the start of where we wrote down the cos 50 equals 10 over x, between that and the answer, all that has happened there is the x and the cos 50, the trigonometry bit, have switched places, and that is always true when you're doing trigonometry. If the thing you're looking for is on the bottom of the fraction, that and the trigonometry swap places. But that's a cheeky approach. I would recommend using the triangles while it's still new. So for the other examples, we would just look at using the triangles. Okay, so example number 3, let's label the sides. So this bottom length here that we know is going to be the adjacent, and x, the side that we're looking for, is going to be the opposite. Okay, so this time we're using tan. So our triangle for tan is TOA, and we're looking for the opposite. So cover that over, and that would tell us that we want the adjacent times tan of the angle. So 12.1 tan of 73. And again, if we just whack that straight into the calculator and press equals, we will get our answer. Okay, example 4. So our angle has moved places. We're now dealing with the one at the top of the triangle. So be careful with when your angles are in different places to what you are necessarily used to. So again, let's label. So this 5.9 down here is the opposite, and the x is the adjacent. So again, we're playing with tan. So we got TOA. And this time we're looking for the adjacent. So if we cover that over, we would get the adjacent is equal to the opposite divided by tan at the angle. So 5.9 divided by tan of 46. Okay, and then again, whack that in your calculator and press equals. Jobs are good in. Okay, example 5. Let's label our sides. So x is going to be the hypotenuse, and this 9.8 down here is going to be the opposite. So we're using sine, so we got SOH, and we're looking for the hypotenuse. So cover over the h, and we're left with O over S. So that tells us the hypotenuse is equal to 9.8 divided by sine of 67. And again, at that point, smash that in your calculator, press equals, jobs are good in. Okay, one more. So, as always, let's label our sides. So we got the hypotenuse kicking around up here, and then we got the adjacent over here at the side. So we're using cos, so our triangle CAH. We're looking for the adjacent. If we cover that over, we would get cos theta times h, or h cos theta. So then we know the adjacent is equal to 15.5 cos of 23. Okay, and again, finally, smash that into your calculator, press equals, and job is a good one, guys. That's trigonometry in right angled triangles. So I hope you found that useful. If you have, hunt me down on Facebook or Twitter, Maths with Mel. You can always send me requests. You can send me any feedback you like. And also don't forget to subscribe to the channel so you don't miss any updates. Cheers, guys.